Hi everyone, welcome back. We are on the third iteration of Meet the Clades or Meet the Critters. Today we're going to be talking about arthropods and microfossils. So these two are of course not necessarily, we're not talking about these in evolutionary groupings, or otherwise this would make very little sense, but we're just talking about two major groups today. So we'll talk about the arthropods first, and here is possibly one of my very favorite cartoons ever of how many trilobites can the new smartphone hold. Ha. All right, so phylogeny of the Animalia. Again, we've talked about the sponges, the comb jellies, the true jellies. We've talked about echinoderms now, and bryozoans and brachiopods. So the major groups that we have left to talk about are going to be the mollusks, which will come next, arthropods, and then we've got the hemichordates and the chordates, which will come a little bit later in the semester. Arthropods make up approximately 80% of extant animals today, mostly just insects. But apart from trilobites and crustaceans like lobsters and crabs and other things, their fossil record really kind of stinks. And there's a whole bunch of subgroups in here. So the trilobites, the arachnids, like the spiders, the millipedes, the insects, and again, the crustaceans. But literally, insects are just that. Out of everything we've looked at so far, insects are just this out of still living animals today. So insects are wildly successful. Think about that when you think about those cockroaches, huh? They are winning evolution. So Arthropoda means jointed limbs, and they show up in the Cambrian, possibly representatives in the Ediacaran. So Parvancorina is a possible Ediacaran arthropod. I really don't have any information to say for sure at this point, but how we identify them is a segmented body and jointed limbs. They have a chitin exoskeleton, right? We've talked about that during the biomineralization lecture. Sometimes it's strengthened with either calcium carbonate or calcium phosphate, like trilobites have it sclerotized with calcium carbonate. And they're present in pretty much everywhere, meaning the land, air, and water. Amniotes are really the only other animals to have achieved that, and amniotes are things that are cooked in an amniotic egg, so you're looking at mammals and reptiles there. So here's an example of that jointed body. All right, so we have the three parts here. The names of these actually change depending on what arthropod group you're talking about. They're all fairly homologous terms, so they should be the same, but at this point they're not. All right, so we've got some version of the head, the thorax, and the abdomen. For example, in a trilobite, this is the cephalon, the thorax, and the pagitium. All right, so we'll move on here. Let's talk about the trilobites. The trilobites are some of the most famous fossils, photogenic fossils. So this is an example of one found from Morocco. They can be absolutely exquisitely preserved. Here is a spine coming off of the forehead area called the glabellum. Here are the eyes. These eyes are positioned in a really excellent way to see things. There are spines all over this, likely for protection. So we'll talk more about the different morphologies that we can see in trilobites both now, and they have a fossil record from the Cambrian to the Permian, trilobites. However, they really never got their groove back from the end Devonian mass extinction. They really just did not come back from that. They have calcified exoskeleton, which means they have really good fossils, and if you'll remember, they also molt, which we've talked about, which means they leave behind more than one fossil in their lifetime. They were likely detritivores, meaning they weren't really active hunters or anything. They were kind of just scooping up trash on the seafloor. Mostly benthic, meaning they were hanging out on the seafloor, although some possibly were swimming or floating around. They can be tiny, from 1 millimeter, to literal dog-sized, like Isotelus rex. Here is Isotelus rex. Holy mackerel, I believe the largest one is about 16, 17, 18 inches in length. You can see one of the most famous specimens at the Cincinnati Museum Center in Ohio, if you are looking for a fun vacation spot. So Trilobite morphology, as I said earlier in the beginning of the lecture, we have the cephalon, the thorax, and the pagitium. Now, a lot of people think that this is where the tri comes from, these three parts, but that's not the case. It has three lobes, the two pleural lobes out on the sides, and the central lobe. So that's where the trilobeite comes from. There's some other things that we'll talk about, but here are the eyes, The glabella, which is the space between the eyes, Latin for forehead, for fun nonsense knowledge that you needed in your life, right? It has facial sutures and free cheeks. Now go ahead and take a look at the trilobites in your fossil kit. Pause this video, go grab your fossil kit, and go take a look at the trilobites. One of the questions I asked you in your taphonomy lecture assignment was, why did it look like these parts of the head were chopped off? Well, the answer has a very simple explanation, and we'll talk about that in just a second, but think about it for now. Here we have our Pagitium, our Trilobite Morphology. One of the major trends that we see through time is the shape of the Pagitium. All right, so the Pagitium is this end piece here. There's 3 different terms. I'm not going to ask that you memorize these, but here's some examples of evolutionary trends. We have macropygus, meaning the Pagitium is actually larger than the head. We have isopygus, so just like isometric, meaning that all the crystal axes are the same length. Iso means same size. And then finally, we have micropygus, meaning you have a small butt compared to your head. What we see through geologic time is we see a preference for micropygus organisms. Not really sure why, but we do. Now, again, as I said, we've watched this horrifying GIF before of the Japanese spider crab, and I'm making you watch it again. I'm so sorry. It's really mesmerizing, though, isn't it? Ugh. All right. So, trilobites, like most other arthropods, grow by shedding their exoskeleton, which is called ecdysis. All right? The discarded shells get preserved most of the time. So, how this is working is there are weak points on the exoskeleton that the organism can actually remove itself from. So how lobsters will do this is that lobsters will shed their exoskeleton, and it takes a couple days for their new exoskeleton to firm up. When they first come out, they have very soft, delicate skin. As you can imagine, this doesn't really help us very much, does it, when it comes to protecting ourselves? It absolutely doesn't. So lobsters, female lobsters, will often crawl into little houses they made out of rocks to hide from predators and other organisms until their new exoskeleton firms up. Trilobites probably did something similar. So why does our trilobite look like it's missing some pieces on its head? Well, the answer's right here. The free cheeks and the fixed cheeks. Here are the fixed cheeks on the inside. The free cheeks can actually pop off, and that's how the trilobite is getting out of its too small exoskeleton. So the reason that you have those missing pieces is because you don't have the trilobite itself. You have one of the discarded molts. Pretty cool, right? Some of you may have a complete specimen as well, but most of you have molts. So trilobite growth will change as the animal grows up in the fossil record. So here is a wee baby trilobite. Here is the head, the cephalon, and here is the Pagitium. You can see there's not a whole lot of thoracic segments here, that middle part. You have the 3 lobes defined well, though, even in infancy. As the organism grows, it usually gets bigger by adding thoracic segments. So we can typically see how old a trilobite would be based on the number of thoracic segments. And my goodness, there are so many trilobites. We can get an excellent growth series. This is a beautiful display down at the Houston Museum of Science. Trilobites have 2 types of eyes. We have holochroal eyes and schizochroal eyes. Holochroal eyes are close, packed lenses covered by a single membrane. All right. This is a lot of what modern insect eyes will look like today. Schizochroal eyes have fewer and larger lenses, typically arranged into some kind of column. So schizochroal eyes are typically found in juvenile trilobites, whereas holochroal eyes are typically found in adults. Some trilobites do also contain schizochroal eyes into adulthood, and that's an interesting trend called paedomorphosis, meaning emphasis on juvenile features into adulthood. That's something we'll talk about in a little bit when we talk about evolutionary trends. But a lot of critters will actually retain juvenile features. So thinking about humans, maybe a short stature or large eyes, rounded face, things that we typically see in juvenile humans as well. So trilobite eyes also have a fun party trick. They're made of calcite. So each of these lenses is made out of calcite. Let's review some of the properties of calcite. First, it has 6120 cleavage, it has rainbow refraction, right? High birefringence, none of that is important here. I just wanted to bring up some mineralogy in case you were missing it. But it also has a really fun party trick in that it can double refract light. So in one certain angle, and that angle is going to be, well, in most angles except for down the C-axis, you will actually look through a piece of calcite, just like this lovely calcite crystal here with 6120 cleavage, you will see double. Now, if you are trying to escape a predator, seeing double is probably the least helpful thing you can imagine. Trilobite eyes are actually all oriented down the C-axis. If you'll remember, calcite has a specific hexagonal crystal system, which means A1 equals A2 equals A3 does not equal C, meaning C is the only one of those four axes that is a different length, and it is oriented down that C axis so you get rid of all of the double refraction. There is your fun fact for the day. Other these are trilobites, these are not echinoderms. Okay, they're pretty cool though, so never mind, we'll just continue. Alright, so we can also see some really cool adaptations to rolling. We'll learn more about these in our in-class assignment. Spines for protection, and even sunshades. You see this curling over here at the top? This is actually protecting the trilobite from too much sun. A lot of scientists assumed that trilobites were all nocturnal. This is evidence to reject that hypothesis right there. Why would it evolve essentially sunglasses to avoid sun if it was nocturnal? There's some really cool rolling. There's a whole bunch of different shapes of trilobites, and these can correspond to different types of environments. A lot of this is homoplastic, meaning they evolved a whole bunch of times independently. We'll learn more about this in our in-class assignment, though. Moving out of the trilobites, here we have the Chelicerata. Chelicerata are things like spiders, scorpions, mites, horseshoe crabs, which are still around today, and Eurypterids, which are all aquatic. Here is a Eurypterid. This is a completely extinct group. They could be holy mackerel gigantic. I have stood next to an example of Pterygotus over in the Czech Republic, I believe, and it was absolutely terrifying to look at. Can you imagine swimming up next to one of these? This is an unsuspecting person just under 6 feet tall. They live from the Ordovician to the Permian, and they are the state fossil of New York. Centipedes and millipedes. So these are the first body animals of something that is found on land. So this here was one of the very first things found on land. The trackways have been found since the Ordovician. However, the first body fossil so far has been found in Silurian times. They got absolutely giant in the Carboniferous, over 6 feet in length. Again, terrifying. We'll talk more about why that is later, or in a few minutes. So they also got large, insects also got large about the same time as the millipedes did. So here is a massive dragonfly that was larger than your head. Again, thank you, extinction. Let's never bring that back. Here is a beautiful insect found preserved in amber, which is one of the only ways we'll get these delicate features like the actual legs here with all of the little hair sticking off of them. Insects likely got so successful because of flowering plants. So a lot of different relationships were likely born out of flowering plants that sped up speciation. So why did the insects get so big? This is a question fueled by nightmares that we all need the answer to. So in the Carboniferous time, we see a spike, an incredibly large positive excursion in carbon-13. From what we know, that means there was an explosion in photosynthetic activity right here. That is where trees evolved. Trees started producing lots and lots and lots of oxygen. Kapow, we have a massive amount of carbon-13 in our environment. We have lots of oxygen, and that is likely spiking the insect trend in body size. Crustaceans. This is the last major group of arthropods we'll talk about. Crabs, lobsters, shrimps, woodlice, barnacles, and ostracods. Very exciting. Here is a fossil crab. They make the cutest fossils. Oh my goodness. There is a really cool video here that you should go watch of a crab fossil being prepared out of rock. Barnacles. Barnacles may look kind of boring, but they actually have really exciting lives. They are actually able to take their reproductive organs and sling them out onto the sea floor where other fish can actually accidentally chomp them in half, and the barnacles are like, meh, whatever. They keep going. They actually have really wild lives. So, Charles Darwin, the, quote, father of evolution of the evolutionary theory of natural selection, says, "I hate a barnacle as no man ever did before." That was after he wrote a 450 some odd page book on barnacles. Poor life choices, Charles Darwin. Here is the inside soft tissue part of a barnacle. Please take a look inside your fossil kits to find your barnacle. It is probably broken and not great shape, but that's okay. Ostracods. These are microfossils. However, they're still really cool to look at. So they usually look like capital Ds, like the letter D, as you can see that shape here, and they kind of look like bivalves, like clams. They're not. They're definitely arthropods. They live on the seafloor typically or in fresh water, but again on the floor of that. They're incredibly valuable for paleoenvironmental tools and for understanding reproductive techniques. Ostracods have extremely varied reproductive techniques, including being able to switch sex from male to female and back pretty much by snapping their non-existent fingers. They're pretty cool. So we're going to pick back up with microfossils here in the second part of this lecture. See you in a minute.